Hello everyone. Once again, welcoming to the lecture series on antenna. In last two lectures, we had discussed about basic concepts of antenna, in which especially we had completed definitions of antenna. Also, we had completed some of the parameters of the antenna, in which especially how electromagnetic wave will be radiated from antenna to the free space. It is discussed in the first lecture or last two lectures. Also, we had completed the radiation mechanism of antenna. So, in today's lecture, we are going to discuss the radiation pattern of the antenna. This is the most important parameter, that is fundamental property of the antenna. So today we are going to discuss about the radiation pattern of antenna. Also we will discuss the radiation lobes of the antenna, and third point is that we will discuss about omnidirectional, directional radiation patterns of the antenna. So I am Mr. S.S. Barkade, Assistant Professor, Department of Electronics, Yashwantrao Chauhan Institute of Science, Satara. So let us go to the concept directly. So first point is that fundamental parameters of antenna, in which especially radiation patterns. Now what is the definition of antenna? Especially it is discussed in last two lectures. So antenna is a device, it is metallic device specially used to radiate or receive electromagnetic signal. Okay. So now, how electromagnetic signal, in which pattern electromagnetic signal is radiated from antenna to free space? What is the exact pattern? What may be it? So the definition of radiation pattern is that a mathematical or graphical representation of the radiation properties of the antenna as the function of space coordinates. That means an antenna radiation pattern or antenna pattern, it can be defined as a mathematical function or graphical representation of the radiation properties of antenna as a function of space coordinates. We know that there are different space coordinates. It will be discussed, it should be discussed into the next some diagram. It is clear according to your diagram. Now, in most of the cases, the radiation properties or radiation pattern is determined in far field region. Especially, it is determined in far field region. This is your far field region especially, and it represent as a function of directional coordinates. Directional means direction of the signal which is transmitted from the transmitter toward any object. That means what should be the direction of the electromagnetic signal from antenna toward into the free space. Okay. Now the radiation properties, this radiation properties includes number of points, in which especially power, that is power flux density, then radiation intensity, this is power flux density, radiation intensity, then field strength, then directivity, phase and polarization. These are all the properties of that particular radiation pattern. So a single radiation pattern which is transmitted from the antenna toward the free space, it has its own properties, and that properties are power flux density, radiation intensity, field strength, directivity, phase or polarization. So these are the properties of that particular radiation pattern. Now the radiation properties of most of the concern is that 2 or 3 dimensional spatial distributions of radiated energy as a function of the observer's position along a path or surface of constant radius. So each and every radiation pattern has its own resistance, okay, own radius, and each radius may be constant or it may be different. Now a convenient set of the coordinates can be seen by using this diagram. So you can observe that this is the coordinate system for an antenna analysis, in which when radiation pattern is derived from the antenna, at that time there is a coordinate system is present for the antenna analysis, in which a trace of received electric and magnetic field at the constant radius is called the amplitude field pattern. Or on the other hand, a graph of the spatial variations of the power densities along to the constant radius is called as the amplitude power pattern. So these are some definitions related to the amplitude power pattern and amplitude field pattern. So amplitude field pattern is that a trace of received electric or a magnetic field at the constant radius is called the amplitude field pattern. On the other hand, a graph of spatial variations of the power density along to the constant radius is called as the amplitude power pattern. Now we are going to discuss the coordinate system for an antenna analysis. Now see carefully, this is your coordinate system, in which this is the main lobe of that particular radiation pattern, and each and every main lobe has some minor back lobes are present. This main lobe is called as major lobe, but some minor lobes are present out to the opposite side of this major lobe. Now you can see that this is your major lobe, this is your minor lobes. These are called as back lobes, and this major lobe are called as main lobe. Now there are 3 different coordinates are present. That coordinates is known as Cartesian coordinate, that is x, y and z. In your electromagnetic signal, which is radiated from the transmitter or which is radiated from the antenna toward the free space, when it enters into the free space, now at that time it has its own radiation pattern, and each and every radiation pattern has a main lobe and number of back lobes, and that's back lobes are known as the minor lobes. Now when we consider this point as the center of this particular lobes or this particular pattern, at that time there is 3 different coordinates, that is x, y and z. Now at that particular 3 coordinates, there is one is the direction of propagation. For example, now your z is the direction of propagation of electromagnetic signal. At that time electric field may be present along to the y-axis and magnetic field may be present along to the z-axis. That means these 3 coordinates are perpendicular to each others. They creates 90-degree angle with respect to each other. For example, this is the 90-degree angle. Now x is generated 90-degree angle with respect to y. Now y is generated 90-degree angle with respect to z, and your x also generated a 90-degree angle with respect to the z. That means these are the 3 different coordinates which are perpendicular to each other. One is occupied field of direction, or direction of propagation, another one is occupied electromagnetic field, electric field, and third one is related to the magnetic field. Now this is related to the coordinates and the relation between three different coordinates. Now the R is the radius of that particular coordinate system analysis, and now these two different R, that is, we analyze a small portion in that particular coordinate system. That means from this lobe we consider only a small portion, and we are calculating the radiation power, radiation field pattern. We can calculate for this short part, and finally we can integrate this part and we can calculate total radiated power in a major lobe or total radiator field of that particular major lobe by using this. Also, when we calculating the radiation power or radiation field for this small portion, at that time that small portion also have three different coordinates, and these three different coordinates is known as other than Cartesian coordinates, and that are, it can be calculated by using direction of propagation, then a radius, and then angle generated by the x-axis or angle generated by the z-axis or y-axis with respect to that particular area. So this is your phi, and it is known as the azimuth plane, which is generated with respect to x coordinates by your radius of that particular portion. This is your total area occupied by that particular portion along to the x-axis, and this is along to the y-axis. So this is the area particularly occupied by that particular area, and now this is called as the azimuth angle. Now this is azimuth angle, and at the opposite side of this there is a elevation plane. This is elevation plane. The plane between plane between x and z is known as elevation plane, and the angle is theta, which is generated in between direction of propagation, that is a z coordinate, and r sin theta, the theta portion, and this is your theta angle. Now this area is occupied d theta space and also r d phi and r d theta. Now these coordinates is known as a phi r into er, that is electric field strength, and h, that is magnetic field strength of that particular coordinates. Also there is a second coordinates, it is unit vector of the a phi in the bracket electric field along to only that particular phi angle, and this is the magnetic field of only that particular phi angle. And third one is related to the third axis, and it is unit vector of the theta coordinates, and this is the electric component which is related to theta, and this is magnetic component which is related to the theta. So there are three different components, that is theta, phi and r, and these three components are totally different than each other. That means a single area of that particular lobe has three different components, in which when direction of propagation is z, at that time z component is equal to 0 and other two components are present in that particular coordinate system. Now when we calculated this area for that particular small portion, it can it is final answer should be r square sin theta d theta and d phi. This is your final area for that particular sum portion. Now when we integrating this equation for this particular lobe, at that time we can calculate the total area occupied by that particular major lobe. Okay, according to this we can calculate this. Now obtain the field and power patterns are normalized with respect to the maximum values, yielding the normalized field and power patterns. Also, the power pattern is usually plotted on the logarithmic scale and more commonly in a decibel. Okay, this scale is usually described because of the logarithmic scale can accentuate in more details those part of the pattern and they have very low values, which later will be referred to as minor lobes. For an antenna, there are some assumptions are present, in which first one is for the field pattern, second one is for the power pattern, and third one is also for the power pattern. But two power patterns are for the two different scales. One scale is linear scale, another scale is in dB. Now, for an antenna, number one point is that the field pattern in a linear scale typically represent a plot of the magnitude of the electric or magnetic field as a function of the angular space. This is the first point related to the linear scale with respect to the field pattern, which is typically represent a plot of magnitude of electric or magnetic field as a function of the angular space. Second one is the power pattern in linear scale. Now typically represents a plot of the square of the magnitude of electric or magnetic field as a function of angular space. Now, what is the difference between power pattern and field pattern? See carefully, it represents plot of the square of the magnitude only. What is slight difference? It is the square of the magnitude only, but it is the magnitude only of the electric or magnetic field, and it is a function of the angular. Both are the function of the angular space, but there is a slight difference. Power pattern is the only magnitude of the electric or magnetic field, but field pattern is the only magnitude of electric or magnetic field, but in power pattern it is a square of the magnitude of electric and magnetic field. Is that clear? What is the difference? Now, third one is that power pattern in dB. Now, power pattern in dB is represent the magnitude of the electric and magnetic field in decibel as a function of the angular space only. There is a difference. It is similar to the field pattern, but it is measured into the dB. Now there is no square of the magnitude of electric and field as like power pattern in linear scale. When we calculate the power pattern in dB, so there is similar to the field pattern, but the measurement scale is in dB. Now to find a point where the pattern is achieved, its half power means minus 3 dB point. It is relative to the maximum value of the pattern. You set the value of the number one field pattern at 0.707 value of its maximum. It can be seen into the next diagrams. You can see there is a power pattern, so we can multiply by using 0.70. Okay, and this is your 0.707. Then next one is power pattern in linear scale at its 0.5. This is your 0.5 at its 0.5 value of its maximum as shown in this figure. And the third one is power pattern in dB at minus 3 dB of its maximum as shown in this figure. So this is your minus 3 dB power patterns. Now, to demonstrate this two-dimensional normalized field patterns plotted in linear scale, power pattern plotted in linear scale, that is field pattern plotted in linear scale, field pattern plotted in linear scale, now power pattern plotted in linear scale also, and power pattern plotted on log algorithmic dB scale, log arithmetic dB scale of a 10 element linear antenna array of isotopic sources with a spacing of d is equal to 0.25 lambda, with spacing 0.25 lambda. So this is two-dimensional normalized field pattern with linear scale, power pattern linear scale, and power pattern in dB of 10 element linear array with spacing of the d is equal to 0.5, that is 0.25 lambda. Now, between the element in this and subsequent pattern, the plus and minus sign, this is your minus sign, this is your plus sign. This plus and minus sign in the lobes indicate that the relative polarization of the amplitude between the various lobes, which changes, which alters as a null are crossed. That means they can be cancelled to each other. There is a null are crossed. Now, to find the points where the pattern achieved its half power, that's at minus 3 dB power point related to the maximum values of the pattern, you can set the different values, and that different values may be for the field pattern this value may be 0.707, and for the power pattern this value may be 0.5, and for the power pattern in dB this value may be set at the minus 3 dB. So these are the three different diagrams which is related to the field pattern, power pattern in linear scale, power pattern in dB scale. Now, all three patterns add the same angular separation between the two half point, and this angular separation is 38.64 degree. Okay, this is the angular separation in between two points, and it is nearly equal to 40 degree, and it is exactly 380.64 degree. Okay, these are the angular separation for the half power. Now, on their respective patterns referred to as half power beam width and illustrated in the figure 2.2, this is your figure 2.2, this is discussed. It can be discussed in later once again. And now in practice, three-dimensional pattern is measured and recorded in the series of two-dimensional pattern. However, the most of the practical applications, if you plot of the pattern as a function of theta for some particular value of phi, and plus a few plot as a function of phi for some particular values of the theta, and it gives most of the useful and needed information. So this is all about radiation patterns, in which field pattern in linear scale, power pattern in linear scale, and again power pattern in dB. Okay, so this is all about the half power beamwidth. It can be referred as half power beamwidth. Now, the next point is that radiation pattern lobes. Now, we had seen that a radiation pattern has different types of lobes, in which specially I said that there is a minor lobe, there is a major lobe, there are a number of lobes are present. Now, various part of the radiation pattern are referred to as lobes. So which may be subclassified into the major or main lobe or minor lobe or side lobe or back lobe. There are maybe 4 different types for the lobes. Now a radiation lobe is a portion of the radiation pattern bounded by a region of a relatively weak radiation intensity, and it can be demonstrated by figure. How can be it defined? So this is your figure. Now portion of the radiation pattern bounded by the region of the relative weak radiation intensity. That means the radiation intensity, that maximum radiation intensity is gathered at the center of that particular lobe. However, we travel from lobe center to outward the lobe, at that time the radiation intensity, that is radiation intensity, is decreased with respect to the covered distance by the signal. Okay, so your radiation, we consider weak radiation intensity as a boundary, as a region of that particular relative weak radiation intensity, and it can be demonstrated symmetrically 3-dimensional polar pattern. This is your 3-dimensional polar pattern. A number of radiation lobes are present in this particular. So you can see that these are the number of radiation lobes. This is main lobe, this is minor lobes, and this is back lobe. Okay, these are the different types of lobes. Now some of them are greater radiation intensity than other, but all classified as now major lobe has greater radiation intensity, and these minor lobes are lower radiation intensity. But whatever the radiation intensity, these all are classified as lobes. Okay, these all are classified as lobe. So now we can discuss this one by one. See, this is your first null beam width. This is your first null beam width. That means whole radiation pattern is considered as a beam width. That means maximum radiation intensity which is traveled toward the destination, it can be calculated by using from this 0 point. This is your first null beam width of that particular major lobe, and that there is we cannot be drop any signal from which is radiated from that particular source to destination. Now second one is the half power beam width. Now half power, as we discussed, half power beam width, this is the 2 center point of that particular beam, that is 0.5. So this is your half power beam width. It can be measured into the angle. Okay, so these are the 2 beam widths which are maximum time calculated into the radiation pattern. These 2 points. Now this is known your major lobe. This is your x-axis, this is your y-axis, this is your z-axis. These are the 3 different Cartesian coordinates. Along to that particular coordinates, we can study the 3-dimensional lobe. Okay, these are the lobes. Now these all are the minor lobes. This is a minor lobe, this is a minor lobe, and this is known as the side lobe also. Now these 2 are also minor lobes. These all are minor lobes, but the lobe which is present at the opposite side of the major lobe, and this lobe is known as this main lobe, and opposite side of main lobe is present a lobe, that is minor lobe, is known as back lobe specially. So these are the different types of radiation lobes and beam widths of an antenna. So these are the 2 different beam widths, and these are the minor lobes. side lobes, and also these are minor lobes, and these are the back lobes. So these plus and minus symbols are shown the zero crossing of that particular electromagnetic signal. So this is all about which is related to the lobes. Now, when we discussed the linear plot of the power pattern and its associated with the lobes and beamwidth. We had discussed that there are plus minus symbols. This is your first null beamwidth. This is your half power beamwidth. This is your radiation time intensity aligned with the z direction. This is your angle. This is your time constant, phase, and this is your back lobes. This is your side lobes, and this is also last one is minor lobes. Now we are going to discuss MATLAB based program which is specially designed for that particular lobe systems. Now in that particular diagram we discussed radiation lobes and beamwidth for an antenna pattern, and in this diagram we have discussed linear plot band power pattern and its associated lobe and beam widths. So when we discussed MATLAB based computer programs for that particular radiation lobes, when it is designed as a polar and spherical have been developed and are included in different programs. This program can be used to plot the two-dimensional patterns, both polar and semi-polar, both polar and semi-polar. In polar form, the spherical three-dimensional pattern, it can be a linear or it can be a dB scale. A description of those programs can be found in that particular book, which is written by the Balinese, and that book is Antenna Theory. You can we can design a different types of MATLAB programs for that particular radiation patterns, and for this you can refer a Antenna Theory book which is written by the Balinese. Now a major lobe, it also called as the main lobe, is defined as the radiation lobe, it containing the direction of maximum radiation. That means maximum radiation intensity present into the major lobe, and it is this is your major lobe, and it contains maximum power of the energy, that is intensity. Now you can see that theta is equal to 0 in that particular direction in some of the antennas. In some of the antennas, such as split beam antenna, there may exist more than one or major lobes. That means a radiation intensity, some antennas has number of major lobe also. That means a single antenna can be radiate maximum energy in two different directions also. Okay. Now a minor lobe is any lobe except the major lobe. That means another all lobes are known as the minor lobes. Now what is the back lobe? Now back lobe is a radiation lobe whose axis makes an angle of approximately 180 degree with respect to the beam of the antenna is known as your back lobe. Here is your back lobe, and it generates 180 degree angle with respect to that particular main lobe or direction of propagation. That means with respect to the beam of the antenna. Usually it refers to a minor lobe that occupies hemisphere in the direction of opposite to that of the major or main lobe. Is that it is related to the major lobe and minor lobe. Now minor lobe usually represent the radiation in the undecided direction. Okay, minor lobe represent the radiation in the undesired direction and they should be minimized. They should be minimized. Now side lobes are normally largest of the minor lobes. The level, that means there are number of minor lobes, but which is the side lobe? So minor lobe usually represent radiation in undesired direction, but they should be minimized, and now side lobe are usually normally largest in minor lobes. The level of the minor lobe is usually expressed as the ratio of the power density in the lobe in question that the major lobes. This ratio is obtained termed the side lobe ratio and side lobe levels. Okay. Now side lobe level is which is equal to the minus 20 dB or similar or smaller are usually not desirable in most of the applications. Now, when attainment of the side lobes, smaller side lobes level smaller than the minus 30 dB usually requires very careful design and construction in most of the radar systems. It usually designed in most of the radar system, and a low side lobe radiations are very important to minimize the false target indications. To minimize the false target indications, low side lobes ratio are very important through the number of side lobes. Now, a normalized 3-dimension far field amplitude pattern plotted on the linear scale of the 10-element linear antenna array, which is 10-element linear antenna array we discussed in the first. This is the 10-element linear antenna arrays. Now, at that time, D is equal to 0.25. Your D is equal to 0.25 lambda, and propagation phase shift beta is equal to 0.6 pi between the element as shown into the figure C. This is the normalized 3-dimensional amplitude field pattern in linear scale of the 10-element linear array with uniform spacing of D is equal to 0.25 lambda, and propagation phase shift is equal to beta is equal to 0.6 pi in between elements. Now this is your theta, this is your phi, and now this is your 3 different components of the electric field, that is ER, that is E phi, and that is E theta. Now this is your Z is the direction of propagation. This is your E electric field, and this is your Z, it can be your magnetic field. So these are the normalized 3-dimensional amplitude field patterns in linear scale for the 10-element linear array antenna with a uniform spacing of 0.25 lambda, that is equal to D, and propagation phase shift beta is equal to beta is equal to minus 0.6 pi between the elements. Now, it is evident that this pattern has one major lobe, 5 minor lobes, and one back lobe. The level of the side lobe is about minus 9 dB. The level of the side lobes about minus 9 dB, which is relative to the maximum. A detailed presentation of array will be discussed in next lecture. Before going to discussion, for an amplitude pattern of an antenna, there is 3 different components, that is electric components are present, that is ER, E theta and E phi. At each observation point on the surface of the sphere, there is a constant, that is R is equal to RC, which is shown into the first diagram, that is figure 2.1. In the far field region, radial ER component for all antennas is 0, radial ER components for all antennas are 0 because it is the direction of propagation. Okay. So as compared to others, one or both or other two components, some antennas depends on their geometry and also observer distance may have only one, two or all three components. In general, the magnitude of the total electric field would be, it can be equal to E is equal to, that is capital E is equal to in square root ER square plus E theta square plus E phi square, and it is the your radial distance. Okay, and it is similar one and represent by using magnitude, that is in mode E. So this is all about radiation pattern lobes. So now in today's lecture we have discussed a different radiation pattern definition, that is a field pattern in linear scale, power pattern in linear scale, power pattern in dB, then radiation pattern lobes. Then in radiation pattern lobes there are different types of lobes are present: major lobe, minor lobe. In major lobe there is a maximum radiation intensity is present. In minor lobe there is minimum radiation intensity is present. Now each and every radiation intensity or each and every lobe has its three different components, that is three electric component, three magnetic component, that is three component is that ER, E theta, E phi, which is related to the direction of propagation and also azimuth angle and elevation angle. So this is all about the radiation pattern. So now next point is that the next one is the isotropic, directional and omnidirectional pattern. Now also this pattern is most important. These are the shapes of that particular pattern. Now the isotropic radiation pattern, this is your circuit diagram. This is your demo diagram for the principle of electric and magnetic plane patterns for an pyramidal horn antenna. This is your pyramidal horn antenna. This is your signal radiated from the horn antenna. This is your major lobe and these are the side lobes or minor lobes. Now this is the direction of propagation X, this is the H magnetic field, and this is the E, which is known as the electric field, and they are perpendicular to each other also. Okay, so it is your E plane and this is your H plane, and this is your direction of propagation in that particular lobe. That means a single lobe consists of electric field as well as magnetic field as well as direction of propagation. That means in 3 dimensions it has 3 different coordinates, that is X, Y and Z. Is that clear? So this is your Z direction, this is your Y direction. Along to the Y direction there is a EH plane. Along to the Z direction there is a E plane, and along to the X direction this is the direction of propagation. Now in that particular lobe, the E electric field and magnetic field for the EX is equal to 0 because the direction of propagation is 0. Now your EX is always equal to 0 at that condition, and also similarly Hx is always equal to 0 because these 2 components are present at the direction of propagation. Now this is your H field aperture distribution and this is your E field, that is vertically aperture distribution. This is all the distribution related to the direction of propagation of the signal. Now how isotropic, directional and omnidirectional patterns can be identified. Now there are 3 different patterns are present: isotropic, directional and omnidirectional. An isotropic radiator is defined as a hypothetical lossless antenna having equal radiation in all directions. Suppose we are present here, this is your antenna, and we radiated equally in all direction. So this is your radiation. this may be from up to the here. This is your isotropic radiation. That means energy radiated from center toward any destination in equal form. That means in all direction. The hyperbolic lossless antenna having equal radiation in all directions. So it is known as the isotropic radiator. After isotropic radiator, there is another one. Radiator is present, and which is known as the directional antenna. Now, directional antenna having properties of radiating or receiving electromagnetic waves more effectively in some direction only than other direction. For example, I am a antenna and I receive the signals which is present in front of me, but I cannot receive signal from back side of me. So the signal receiving strength of antenna is particularly in a single direction than other direction. That means it is greater than other direction. That means more effectively it can be received or it can be direct a signal from some direction than other direction. Now third one is omnidirectional antenna pattern. In omnidirectional, having an essential non-directional pattern in a given plane, in this case of azimuth, and a directional pattern in any orthogonal plane in case of the elevation. That means given plane as it is, that is in azimuthal, and a orthogonal plane is present into the elevation. Now an omnidirectional pattern is then a special type of directional pattern. It having essentially a non-directional pattern, it is not a directional, is given in a given plane. So these are the three different patterns of the radiation, antenna radiation, that is isotropic, directional and omnidirectional pattern. These are the all three patterns are taken or reference for the antenna. Now a directional pattern is one of the having property radiating receiving electromagnetic wave more effective than others. Okay. Similarly, this is a example for the omnidirectional antenna pattern, in which in omnidirectional antenna pattern we can see that this is diagram 2.6. This is diagram 2.6, and according to this diagram we can calculate the principal pattern of that particular omnidirectional antenna. For a linearly polarized antenna, performance is obtained described in terms of the principal E and H. This is your E and this is your H, that means electric field and magnetic field plane pattern. Now the E plane is defined as the plane containing the electric field vector. E is electric field vector and H is the magnetic field vector and the direction of the maximum radiation. Now E is electric field vector and direction is maximum radiation, and the H is the H as a plane and the plane containing the magnetic field vector and the direction is maximum direction. Although it is very difficult to illustrate the principal pattern without considering a specific example. Now, it is usually practice orient most of the antennas so that at least one of the principal plane pattern consists within the one geometrical principal plane. An illustration of figure 2.5. This is your figure 2.5. In illustration of figure 2.5, these all are discussed, that is electric field and this is your magnetic field. Now the plane XZ plane, that is elevation plane. XZ plane, that is X and that is Z, and this plane known as elevation plane, and this elevation plane, that is your phi is equal to 0, and the principal E plane and the XY plane and XY plane, that is your theta is equal to pi by 2. Theta is equal to pi by 2. Now is the principle of H-plane. Now this is the principle of H-plane and this is the principle of E-plane. Is that clear? This is the principle of E-plane. Now other coordinates can be selected also. Before going to other coordinates, the Omini directional pattern of this figure has infinite number of the principal E-planes, that is elevation planes. Pi c is equal to pi, okay, and the one principal H-plane, that is theta is equal to pi by 2, means it is equal to 90 degree. And this field pattern of the antenna can be also field region of the antenna, that is far field region, and there are different concepts are present and which can be discussed into the next lecture. So all my dear all students, for this antenna lecture series I am using Antenna Theory Analysis and Design book, which is written by the Balnis. I will suggest you that you can refer this book in detail for in detail study. And in next lecture we are going to discuss some field regions and radian and steradian concepts, which is related to the power patterns of the antenna. Then another one is the radiation power density and radiation power intensity in detail. These 3 or 4 points should be discussed into the next lecture. So all of you, I consider that all of you are not missing this lecture series. So I suggest that please go to the website, go to the YouTube channel of your institute, and please see every and go to the every and each and every lecture. So good day and thank you to all.